This is 3i Atlas. A cosmic visitor from another star system, and only the third interstellar object that we've seen come through our local neighborhood. And in the past few weeks, it's been acting strange. Astronomers have watched it suddenly brighten, shifting more towards the blue color, and they've also seen it fire off around 7 jets of gas and dust, some of which actually seem to be pointing towards the sun, and that's not normal, not for a comet, and not really for anything that's orbiting our sun. Because of all this excitement, the internet has exploded. Rumors about fragmentation and non-gravitational course changes. There's rumors of aliens and people saying that this is an object that's been engineered by something else, or perhaps someone else. But before we jump into any of that, I really do want to slow this down for a moment and take it seriously, because 3i Atlas isn't just weird, it's actually a rare opportunity for us to study something that formed around another star, something that's potentially older than our entire solar system. So today I'm going to break down everything that I've been able to find out about 3i Atlas, why it's named the way that it is, where it's coming from, and perhaps where it's going. I'm going to answer all of the questions that you guys submitted on Facebook and on YouTube, and hopefully I won't miss anything. So let's dive in. So before we get into all of the internet theories and all of the interesting stuff that people have been talking about lately around 3i Atlas, let's take a quick moment to actually root ourselves in the basics of what it actually is. The beginning of the name, 3i, it stands for the third interstellar object that we've been able to observe passing through our solar system. The first one was ʻOumuamua, which was discovered in 2017. This was a small and fast object that had sunlight reflecting off of it in a way that suggested the shape was more of a shard or like a cigar than it was a typical spherical comet. It showed no visible coma, no dust, nothing that you would expect from a comet that we would typically see in our solar system. But it still accelerated as it went away from the sun, which is quite unusual. And ultimately that's one of the main reasons why it sparked such a strong scientific debate. The second object was Borisov, or 2i Borisov, that was discovered in 2019, and it was basically the opposite of ʻOumuamua. Borisov looked like a very typical comet. It had a very pronounced coma, it had a tail behind it, and it had lots of water vapor and carbon monoxide pouring off of its surface. Spectroscopically, it behaved almost the exact same as comets that we observe in our solar system, the main difference being that Borisov was actually on a hyperbolic trajectory heading away from our sun. Spectroscopy is just a fancy way of saying that you can separate the light of an object into its components so you can see what something's made of. There's a sort of related method called occultation, which we use to study the atmospheres of planets, including exoplanets. And now that we understand ʻOumuamua and Borisov, we now have 3i Atlas, and it's something in between. It looks like a comet, and it sort of acts like a comet, but some of the details seem to be a little off. The outgassing, the color change, the jet geometry, and then the potential composition of it all seem to be different than what we've seen in comets from our solar system in the past. So it's familiar enough that we can sort of compare it to some of the things that we've found in the solar system before, but it's different enough that we can't make the direct one-to-one comparison. 3i Atlas is the first interstellar object that we have seen actively outgassing. It's unusually rich in carbon dioxide instead of water ice, which is a lot more normal for comets in our solar system. And its coma shows structural complexities that we don't usually see this early on in an observation window. And now that we understand the naming behind 3i Atlas and its predecessors, we can start asking real questions like where it came from, how fast was it moving before we ever even saw it, and how do we know with confidence that this thing actually originates from around another star? So how do we know that 3i Atlas actually came from another star system? Well, there's really two main clues, and together they make the case almost undeniable. The first clue is in its orbit. 3i Atlas moves on what we call a hyperbolic trajectory, which is just a fancy mathematical way of saying that it is not orbiting around our sun. Most objects in our solar system, like planets, asteroids, comets, they follow closed loops, ellipses around the sun. They'll swing around the sun and then go back out to where they came from, and that's the orbit. But a hyperbola is an open path. It comes in once, it curves around the sun, and then it leaves forever. In these closed loop orbits, the key factor is something that we call eccentricity. If the value of eccentricity is less than 1, then it's closed and it is an ellipse. If it's exactly 1, it's actually a very tight parabola. But if that value of eccentricity is greater than 1, then it is an open loop, and it's something where an orbit will not have the object return. It means that it is unbound to the system that you're looking at. And in this case, that's our sun. Well, 3i Atlas has an eccentricity value well over 1. Even if you strip away every other complication, such as the outgassing from the jets, the underlying orbit is still hyperbolic, and that tells us that this thing is likely not from around here. But the second clue is even stronger. Before the sun's gravity had any influence on 3i Atlas, it was already moving at 58 kilometers per second, relative to our solar system. And this is far too fast for any object that we've ever seen coming from the Oort cloud or from the Kuiper belt. Local comets just don't come in this fast, so something else likely had to fling this thing up to the speed that we observed it at well before we actually were able to observe it. When you run this trajectory backwards in time, which is something that astronomers do for every object that we observe, the path doesn't actually point anywhere in our solar system. It actually seems to be pointing towards the thick disk of the Milky Way. And with this in mind, I can't help but wonder 3i Atlas has actually been traveling for millions or maybe even billions of years. So when we say that 3i Atlas is an interstellar object, it's not guesswork. The orbit tells us a story. The speed tells us a story. And together they point to one of the rarest things in astronomy. Something that is truly, unambiguously not from here. Now let's talk about the part of 3i Atlas that has everybody talking. The jets. Because this is where things really start to look strange. Comets make jets whenever sunlight starts to warm pockets of ice beneath their surface. The ice flashes into gas and expands rapidly, and it starts to escape through cracks or vents, lifting dust as it comes out. On a tiny body with very little gravity, those jets can shoot hundreds of meters per second out into space. Most comets have just a few obvious jets. 3i Atlas, on the other hand, appears to have at least 7, and they are not gentle. Some are long, collimated plumes that are stretching millions of kilometers behind the object. But the detail that has astronomers and a lot of the internet puzzled is that some of the jets seem to appear to point towards the sun instead of away from it, which is what's most common. This really is extremely unusual. Normally the side facing the sun is the warmest, so gas vents outward, but solar pressure usually blows that back around the comet, forming the tail. That's why most comets' tails seem to point in the anti-sunward direction. So how do you end up with a jet that points towards the sun? Well, there's a few possibilities for this, and none of them seem to violate physics. The first is uneven surface heating. If a comet rotates in just the right way, the sunlight can warm up a patch of CO2-rich ice as it turns away from the sun, meaning that the jet fires towards the sun before it rotates away. The second reason might be that there are deep pockets of volatile ices. CO2 sublimates at a lower temperature than does water. If 3i Atlas does have buried pockets of CO2 ice near the sunlit side, then it's possible that they could burst outward with so much pressure that it overtakes the solar wind pressure. A third reason could be the local geometry, or the actual surface geometry of the object. If the surface is jagged or sloped, then these gases can be moved around or collimated in directions other than what you might expect from broad-scale heating alone. But none of this implies that the object is steering itself, that it has changed propulsion, or that it is aiming towards the sun. It just means that the internal structure of this thing is complicated. It may be that it's just fractured or layered or has a different chemical composition than any other comet that we've been able to study before. And ironically, the sunward jets actually tell us something comforting. It tells us that this is still a natural object. It's just likely one that formed in conditions other than what we see normally here in our solar system. So we've talked about the jets, but that's not the only thing that people were noticing. 3i Atlas also brightened very quickly, and it shifted towards a blue color. It also became the subject of a lot of theories online about course corrections and about breaking up into different parts. So let's break each of these things down cleanly. First, the sudden brightening. As 3i Atlas moved to its closest proximity to the sun in late October, astronomers watched its brightness rise faster than it was expected. That part is real. Comets brighten when sunlight warms their surface, and any of the ices that are trapped in the surface outgas. That process lifts dust up into the air, and that dust then reflects sunlight. So the more dust that you outgas, or that you loft into the area around the comet, the brighter it's going to appear to be. 3I Atlas likely has a patchwork of ices beneath its surface. When those layers warmed up, they erupted, causing the brightness to increase very quickly. Next is the blue color. The coma didn't just brighten, it actually shifted towards a blue tint. That usually points to very fine dust grains, which have a tendency to scatter the blue end of the light spectrum more. It could also be related directly to carbon dioxide outgassing, which leaves particles behind known to scatter the blue end of sunlight. So yes, the blue color is real, but it does not imply anything other than the chemical makeup of the comet itself. The third thing is the fragmentation rumors, or the rumors that the object has begun breaking into pieces. It seems like every time a comet brightens very quickly, people rush to start talking about whether or not it's broken apart. Right now for 3I Atlas, there's no evidence that this is taking place. If it had cracked into fragments that could significantly impact its trajectory, then we would have already seen this in our high-resolution imagery. What we do see is uneven dust, knots, and clumps inside of what we call the coma. And those can look like fragments when you're looking at compressed and processed pictures. But knots aren't chunks, and we haven't seen anything that shows that any significant breaking up has taken place at this time. The next thing is course changes. This is one of the more persistent rumors that the object has somehow changed its course. But all comets experience thrust from the jets that come out of their surfaces. Those small forces do cause deviations, but we measure these in the hundreds and maybe thousands of kilometers, not millions. But the observed path for 3I Atlas is normal for an actively venting comet. There's nothing abrupt or unexplainable, just calibration adjusted tracking on a very small, faint object. Alright, so where does this leave us? We have a sudden brightness spike, a slightly bluing coma, knot structures in the dust, and subtle jet-like deviations. All of this fits comfortably into the physics of a naturally, actively volatile-rich comet. It's just one that we didn't grow up with, and it looks different than all of the ones that we've seen before. And this brings us to the next piece. Why does 3I Atlas behave this way? What is it made of, and why does it look so much different than the things that did form around our sun? To answer this, we'll look at the composition next. The first thing that sticks out to me is that it is CO2 rich and water poor, which is very unusual. Most comets that we observe locally are dominated by water ice. They also contain CO2, carbon monoxide, and other kinds of ices, but water tends to be the main driver for outgassing whenever a comet approaches our sun. But 3I Atlas seems to flip this ratio. Spectroscopy shows that it's releasing a lot more CO2 than it is water, and that's not normal for Jupiter family or Oort cloud comets. A CO2-dominated comet suggests that it formed somewhere cold, extremely far away from its parent star. Or it might be composed of ices that have just changed over millions and billions of years. It hints that the building blocks of this object come from a place in its own star system that we rarely get to study in our own solar system. It's a zone that must be colder and darker than the regions where our solar system forms its own comets. And the coma structure seems to support this idea. The shape of the coma, the dust cloud around the nucleus of the comet, is not smooth. Rather, it seems to be threaded and patchy and asymmetrical. And this is consistent with a nucleus that has layered or fractured ices, uneven pockets of volatile material, and a surface that's been essentially irradiated by cosmic rays for millions and maybe billions of years. So this thing is old, like potentially older than our solar system. Another clue is polarization. Astronomers also study the way that sunlight scatters off of dust. 3I Atlas shows strong negative polarization, meaning that the light reflects in a similar way as some of our outer solar system planets, but in a much more extreme way. This suggests extremely fine dust particles, possibly processed for ages by cosmic radiation, which could make sense if it's been drifting between stars for such a long time, which it seems that it has been. This is also the first time that we're seeing an interstellar object with active chemistry. ʻOumuamua had no visible coma. Borisov did, but it looked like a standard solar system comet like we've seen before. The 3I Atlas is different. Its behavior is driven by a chemistry that's just simply unfamiliar to us. And the more that we learn about its jet structure, the dust that's lofted up from it, and its CO2 production, the more that it seems to support this one idea. This object was formed in a planetary system that is much different than our own. A different star, a different disk, a different distribution of ices, a different history. And that's exactly what makes studying 3i Atlas such an immense opportunity. It's letting us study the building blocks of another stellar system without even having to send a spacecraft there. And now that we know what it's built from, the next logical question in my mind is, what do we think we could have learned by sending a spacecraft right to it? So now that we know what 3i Atlas is made of, and why it's so different, the obvious question comes up. Could we have sent a spacecraft to intercept it? And if not, what would it actually take to do it? Because it feels like an opportunity, right? It should. It's a once-in-a-lifetime opportunity to study the chemistry of another stellar system without even sending a spacecraft there. But as exciting as that sounds, the engineering realities behind it are pretty brutal. We simply don't have enough time to catch it. And that's only because we discovered it too late for that window. By the time the survey telescopes picked up 3i Atlas, it was already inbound and moving fast, placing it well within a window where mission planning isn't just difficult, it's impossible. To intercept an object moving on a hyperbolic trajectory through space, you would need the following. You would need years of preparation. You would need a waiting spacecraft, so something on standby, ready to go. You need a launch window that you can hit instantly, and you'd need propulsion far beyond what we keep on standby today. The necessary change in speed, something that we call delta V, is just too large. Mission planners estimated that to catch 3i Atlas, we would need something around 20 through 24 kilometers per second of delta V, and that's being very generous. For some perspective, New Horizons, which was our fastest flyby mission, it launched around 16 kilometers per second. Parker's Solar Probe, which is the fastest moving man-made object, eventually reached 195 kilometers per second speeds, but it had to use gravitational assists from Venus multiple times to build up to this speed. Chemical propulsion alone can't give us the velocity change that we need to do something like this. So even if we had a spacecraft sitting on a launch pad at the moment that 3i Atlas was discovered, we simply don't have the propulsion power to perform a maneuver this extreme and in this amount of time. So in a sense, it's not that we really missed our chance, it's that we're not really prepared to take advantage of them at all in the first place. The solution is to have a spacecraft already waiting and ready to go and study these objects as they come. That's actually the idea behind the European Space Agency's Comet Interceptor mission. This is a multi-probe spacecraft that will sit at one of the Lagrange points waiting for a suitable object to pass through our solar system. It's the first mission designed for essentially, we don't know what yet. But if we want to get close to an object like 3i Atlas, I think that that's the way that we would have to do it. But so goes the next question. If we could catch it, what might we learn? I think most of us would agree that if we could reach the object, the science that could be done would be extraordinary, even if it was just a brief visit. We could directly measure its ices, we could look at in situ composition measurements of the dust grains, we could get high-resolution images of the vents and fractures. We would essentially get a first close-up look at another star's debris disk. We could look at isotope ratios to better understand the origin of the materials that it's made of. And ultimately, this might lead us to insights on whether the CO2 composition is a result of where it came from versus millions or billions of years of basically cosmic radiation. It would be like holding a piece of another solar system in your hand. But unfortunately, we're not there yet. And that's okay, because this object is actually teaching us that we need to go ahead and start becoming prepared for this type of research in the future. Now that we know what it's made of, and we've established that we can't chase it down with our current spacecraft technology, another question that comes to my mind is, how often do we see these objects? And then even more importantly, how often do we miss them completely? And the short answer is that it's probably a lot. Our surveys have only recently even become sensitive enough to detect these objects. ʻOumuamua was discovered in 2017, Borisov was discovered in 2019, and Atlas showed up in 2024. But before that, we simply didn't have the technology to detect these faint objects moving along hyperbolic trajectories through our solar system. Most interstellar objects seem to be small, dark, fast, and only visible for a very brief moment of time. So unless a telescope happens to be scanning that patch of sky at the moment that it comes through, it will likely go unnoticed. Modeling efforts on this topic suggest that this could be happening thousands of times a year. Astronomers often run simulations about how many objects from other star systems can be stripped away from their systems and then flung out into the galaxy. And those numbers are enormous. We're talking about trillions of objects roaming around between stars. And statistically, this means that our solar system should be passed by these objects hundreds or even thousands of times every year. But most are estimated to be only a few meters wide. They're too small, too faint, and moving too fast to be detected against the background of space. With the Vera Rubin Observatory now coming online, this detection rate is expected to explode. Instead of one interstellar object every few years, we might see one every few months, and eventually maybe even every few weeks. This is like the universe helping us advance our own science. But even in the scenario where we see these every few months or weeks, 3I Atlas will likely still stand out amongst them. From everything that we know of these objects so far, it's larger, it's more active, its chemistry is stranger than objects we've seen before, its jet geometry is far more complex, and the ratio of CO2 to water truly puts it into a category where it is an outlier amongst outliers. I think that we are extremely lucky that this is one of the first interstellar objects that we've been able to study as much as we have. And now that we know that they're likely common, it brings me to one final question for this episode. What does it mean for something that's older than our solar system to drift right through it only to disappear again, seeming moments later? What questions does that raise about our own meaning? And on the timescales being considered here, what does it even mean to have a life as a human for some small portion of it? We've talked about what 3I Atlas is, why it's strange, and how many objects like it may pass by us unseen. But now I want to slow it down for a moment, and I want to talk about what this means as a human, not as a scientist. Because every time I hear something about an interstellar object coming through our system, it always gets me thinking about what it means to be alive and to be here. When I think about an object drifting between stars for millions of years, untouched and unseen, and bearing the chemistry of a place that we'll never visit, I feel an oddly strange level of comfort. Comfort in being a part of a universe where the distance between young and old can be beyond my ability to comprehend it. Yet somehow we can still be here and be aware of our tiny, tiny place within it. So after all of this, here's the part that feels the most human to me. 3I Atlas is already leaving. It's drifting back out into interstellar space along that hyperbolic trajectory that we discussed. In a few months, it'll be too faint for any telescope to track. And in a few years' time, the trajectory that it's on is going to take it far beyond anything that we could reach anytime soon. And then it'll just be gone. Not destroyed, not finished in any way, just continuing on its journey through the galaxy like it's been doing for millions and maybe billions of years. And to me, that's what makes this whole story feel a lot bigger than just what's in the data. We've got to see something that formed around another star. And we got to ask questions about something that reaches outside of our solar system and far out into the galaxy. And that's at the heart of my intention behind Heavy Brain Space. The idea that science isn't just numbers and math and computer models. It's a way of looking at life from a different perspective. It's a different way of paying attention. A way of noticing the strange things that drift through our own lives, even if we don't notice them right away. 3I Atlas won't come back. Neither will ʻOumuamua or Borisov. These visitors are one-time events, and I choose to think of them as reminders that the universe is bigger and older than anything we could ever imagine. Thank you for exploring 3I Atlas with me. If there's anything that I missed, please put it down in the comments and I'll do my best to answer it there. I'm Jeff, and this is Heavy Brain Space. Cheers.